This call is now being recorded.
So to overcome the memory capacity, we are using push-down automatas. Even still, we are facing some of the problems with Turing PDAs. So computational power is less in the push-down automatas. To overcome that one, we are using the another missions called Turing missions. These Turing missions is invented by the Alan Turing. So the Alan Turing invented this Turing machine before the computers was invented. So it will performs the computational almost all whatever the computations we are doing now with these computers. Almost all computations can be done with these Turing machines. So generally, what is the black diagram of a Turing machine? A black diagram of a FA will looks like this same the thing. Is it so? So it will have the tape and it has one read-write head and it has finite control. Yes, it is also same like finite automatas, Turing machines also. In Turing of machines also we have now one tape and we have the read-write head and we have the finite control mission. So these the things are common, but where we are getting the difference? In push-down automatas, we have input tape as well as read-write head as well as stack and finite control state mission. So that stack will stores the symbols. Grammar symbols will be stored in the stack that is used for extra memory. But now in Turing machine, we are telling it is overcomes the limitations in presented in the PDA also. So it should have more memory. It should has to perform more computation works when compared with the remaining one. But it is looks like a FA. The difference, major difference is here. The tape is of infinite length on the both the sides. So the tape is of infinite length. We can write, there is infinite automatas, there is a finite length of tape. Here it is infinite length. So we can write any number of input symbols. And read-write head, so there we are doing only read operations in the push-down automatas and in finite automatas. But whereas in Turing machines, we can perform write operation also. We can perform write operation also. And also, whereas in finite state machine and push-down automatas, the controller will move to the right-hand side only, on one direction only. Whereas here, the read-write head can move on to the both the directions, on left-hand side and right-hand side. So these are the some of the advantages presented with the Turing machines or features presented with the Turing machines. It has external memory which remembers arbitrarily long sequence of inputs, and it has unlimited memory capability. And this model has a facilitate by the which the input at left or right on tape can be read easily because it can move head, read right head onto the left side or right side. So this is called as Turing machine. So the machine can produce certain output based on in its inputs. In this machine, there is no distinction between input and output symbols. The Turing machine can be thought of as a finite state automata connected to a read or write head. It has one tape which is divided into n number of cells. Here it is divided into n number of cells. Each cell can store one symbol, and the read-write head can examine one cell at a time. These are the common things when compared with the FA. So each the tape is divided into n number of blocks. Each block will store one input, and the read-write head can read one input, one cell at a time. And then a new symbol can be written on the tape in the cell under the head. We can perform read operation as well as write operation. And also we can move this head either to the left or right. Before that, finite automatas and PDAs, it will move only in one direction, that is on the right hand side only. Once if it reads this current cell, the read-write head automatically will move to the next cell. It will read the next input presented on the next cell. Likewise, it will goes. But here in Turing machines, the read-write head can move left-hand side or right-hand side. So there, this is the block diagram of a Turing machine. Coming to the formal definition of Turing machine. As we know that PDA consisting of 7 tuples. So as well as Turing machine will also consist of 7 tuples only. So here Q, sigma, del, Q naught, F are the common the things. Q represents the finite set of states and sigma represents the input alphabets. Del represents the transition function and Q naught is the initial state and F is the final state. So coming to the remaining two tuples, T is one tuple and B is one tuple here. So what is this T and T? T is nothing but the tape input symbols. Here symbols which can be written on tape. So not only we can read this one, we can written onto the tape. So that written onto the tape symbols will be represented on this T. And after once we had read, or if you want to represent, it's a cell is filled with B except input alphabets initially. Every cell, if you read this cell, if you want to represent, we can replace it with the B. That is nothing but blank symbol it will represent. So initially all the cells will be filled with the B. So initially this cell consists of all B's initially. So when we write something, this will be changed as W1, W2, Wn like this. So for representing the cell blank, or we read that cell to representation, we'll use B symbol. That is nothing but blank symbol. So these are the 7 tuples. A Turing machine can be expressed with the 7 tuples, that is Q, sigma, del, Q naught, F. These are the common, and T and P. T represents the tape symbols, B represents the blank. So this is the Turing machine definition. Okay, instantiation description, that is nothing but ID of a Turing machine. So ID of a Turing machine. So present state will take some input. So that is nothing but Q comma A something. After that, what is the output from this state? From this instantaneous description, what is the output? So the output will be the LQR is nothing but tape contents left to the head. What are the remaining tape symbols presented left to this head? And then R is the tape contents of the right to the head of the Turing machine. And then Q is the current state. So what is the left hand side symbols presented and what are the right hand side symbols presented and what is the current state? See here, now here left side, when you read this cell A, the left hand side of this cell is AB. So L is equal to AB and right side it is ABB and the present state it is Q. Same for here, the left side symbols ABB, the right side symbols BB and current state is Q state, Q1. So likewise we can represent. Same the thing, instantaneous description of a Turing machine. Q comma A, present state and input, we'll get Q1 comma. At any given time, the moves of a Turing machine depends on the current state as well as input symbol. So what is the current state and what is the input we are giving? So by depending upon this one, the Turing machine will move. So acceptance and rejection by Turing machine. So it will accept only if a state belongs to the final state, or it will rejects if Q does not belongs to the final state, or else next moves are not defined, or we are going into the infinite loops. then this string can be rejected by the given Turing mission. If either accept or reject, then Turing mission halts. So manaki after performing accept or reject, Turing mission will stops. That condition, that state we are calling as a halt. So Turing mission will halt either acceptance of a language or rejected of a language also. The Turing mission will halt. It will stops. Either it can be in the state of accepted or not in the state of acceptance also. And Turing mission as a language accepted. See here, M mission accepts a string if and only if the execution of M on the string terminating and ends in the accepting state. So we can accept a string. We means in the mission. This Turing mission will accept a state. It will accept a string if and only if it will accept only when. So the execution of mission on string W, either it terminating and ends in the accepting state. Either it should be accepting state or it should end in the if it is accepting state, then the particular string we can tell it as a accepted by the given mission M. At the same time, when the string is not terminating and not ends in the and it ends in the non-accepting state, which means non-final state, then we can tell the string was rejected by the particular mission. So by this particular mission, the string was rejected. So these are the things languages acceptors. And M does not accept a string if and only M rejects or loops on W. So if it is in rejection state or if it is in continuous iteration state or it is in loop state, then it cannot be accepted. See here some of the examples of the instantaneous description. Here Q naught is the some state. We are giving some input to the A, Q naught comma A. Then it is going to the same state Q naught and the symbol you are writing is X and the read write head symbol is moving on towards the right hand side. The last symbol will use the direction, X will use the tape symbol, Q naught will use the state, the next state. Here the first Q naught represents the present state and A represents the input. Same wise Q naught comma B equal to Q naught comma B comma right. So we are taking a state Q naught, it is taking input B. So it will produce the same state Q naught and it will produce B and the read write head is moving towards right hand side. So Q naught comma B comma R. Likewise we have some examples. See here next example Q naught comma B comma equal to Q1 comma B comma L. So previous state Q naught, present state Q1. So previously it is blank. Now tape symbol is also blank. Now we are moving on to the left hand side. Instead of right hand side, we are moving on to the right hand side. So representation, graphical representation of these two things. That's about Turing mission, Alan Turing mission, and instantaneous description of the Turing mission. Is it clear? Is it clear? Next one, representation of the Turing mission. So we can represent a Turing mission by using either transition table or by using transition diagram. As you know, the finite automator can also be represented with transition diagram and then transition table. Same manner we can represent In the same manner, we can represent Turing machine by using transition table or transition diagram. By using both the things, we can represent. See here, del transition function Q naught. So inputs A, B, X, Y, B. So when you give Q naught as input, it has to replace with X, and so we are moving the read write head towards right hand side. Here we are moving read write head towards left hand side. L is there, no? So that represents left hand side. So we have R, so it represents the right hand side. So likewise, we can represent a Turing machine. Design Turing machine to recognize all strings consisting of even number of A's defined over a input alphabet sigma equal to A over the input alphabet sigma equal to A. So now we will see solution for this one. There are three states, Q0, Q1 and Q2. Q0 is the initial state. Q1, by taking A as input, it is moving to the right hand side. And then when you give for A for Q0, we can have this transition diagram. Design a Turing machine that accepts strings belonging to the language 0 plus 1 whole star. See here, 0 plus 1 whole star. Either we can start with 0 or 1, 1, 1, 0, 0, or combination of 1 and 0. We can take so there is no more restrictions here. Simply 0 plus 1 whole star is the sigma or input here. So now Q0 initially it is reading, it can take input as 0 or 1. So it will goes into the same state Q0, and all the two states are going to the right hand side when it is either input 0 or 1. Is there any doubts till now? Is it clear, Ma? Either you can represent by using transition diagram or by using transition table, we can represent the Turing machines. So here, one is the reading symbol and one is the writing symbol. Here, 0 is the input we are giving, 0 is replaced with 0 only. Here, 1 is replacing with 0. So we will perform even write operation also, no? So that's why we can get changes also. And we are moving read write head onto the right hand side. Whereas if the input is blank, when we read input as blank, it has to reach the state QA from so on so state, and it will be replaced with B only, blank only. And once if we reach the end of the tape, in the sense end of the string, we have to come back. So now we have to move our read write head to the left hand side. So that's why here we are taking L. So we don't have right hand side symbol. So we are moving on to the left hand side. So that's why here L is represented. So likewise, some other example, one's complement of a given binary number. For this one, we designed a Turing machine. The Turing machine and the corresponding timetable, corresponding Turing machine transition table. So same the thing, but here we'll get two more attributes. Present state, the next state, and what is the input and what it is replacing. Either you have to move the head either to the left hand side or right hand side. So those are the things only we need to consider. So this is one example. Can anyone explain? These are all examples for this one, transition tables, diagrams and tables. So this is also a Turing machine for the language W power R. So where W belongs to 0 plus 1 whole star. So the next one, variations of the Turing machines. So we have n different types of Turing machines. Multi-tape Turing machine. Before that, we have only one tape Turing machine. Here we have multi-tape Turing machine. For each and every tape, we have one read write head. See here, for all these three tapes, we have three read write heads. So for all the number of tapes, we have a number of heads, read write heads. So that is multi-tape Turing machines. So having multiple tapes where each tape is accessed with a separate read write head. Each head can move independently of the other heads. Initially, the input is on tape 1 and other are blank. At the first step is to occupied by the input and other tapes are kept blank. And then the next, the machine reads consecutive symbols. It will read the consecutive symbols under its head, and the Turing machine prints a symbol on each tape and moves its heads. Depending upon the present state and input symbols scanned symbols on each tape and moves its heads. Depending on the present state and input symbol scanned by each of the head, the Turing machine can change. So the Turing machines can change so it is multi-tape. The next one, multi-heading Turing machine. Before that, we have n number of tapes, multiple tapes. Now, multi-headings. So we may have n number of headers. So n number of headers may be presented. 1, 2, 3, 4, like this. The next one, two-way infinite tape curing. Before that, at one end, it is infinite. So it is a infinite tape on one side, and it is of infinite length on both the sides. Now this is the two-way infinite taping machine. So a Turing machine where there is an infinite number of sequences of blank on both the sides of these tabs is called a two-way infinite tape. So we have infinite lengths on both the sides we can extend. And multi-dimensional tape Turing machine. So we have multi-dimensional. It is two-dimensional width and length. And then non-deterministic Turing machine, as like FAS, PDAs, Turing machines, non-deterministic Turing machines. So the non-deterministic Turing machine a non-deterministic Turing machine has a single one-way infinite tape for a given state and input symbol has at least one choice to move from. So to move each choice, several choices of path that is might follow the given input string. A non-deterministic Turing machine is equivalent to the deterministic Turing machine. Same concepts. So the next one we have universal Turing machines. So the universal Turing machine is a Turing machine that simulates an arbitrary Turing machine and arbitrary input. The universal machine essentially achieves this by reconducting the description of the as well as the input to that machine forms its own space. So recursively enumerable and recursively enumerable languages. So concatenation, if L1 and L2 are two recursive languages, their concatenation will be also recursive. So this is about Turing machines. So this is about the introduction about the Turing machines. So the remaining thing we will see in the next class. It's very important Chomsky hierarchy and then